Start it up. This can come back to that. I think you're on the right track. So it absolutely has to do with that positive definition. Okay, let's come back to the central limit theorem. Last time I went through this really quick, kind of sketched at least the techniques we needed, understood the toolbox that we needed, all the elements. Let me just ask you a question. How many people went through and read the CLT proof in the book? Good, that's what I asked you to do. So, go through all of that, then read through it. If you don't go back through the CLT proof, you just wasted a day. So, you wasted that lecture that I gave you. That's supposed to instill all of the concepts you need to know for the proof. So, I could ask, pop quiz, let's look at the proof. Because I asked you to look at it in the book. Would you be prepared to do that? And to do the proof? You will need to be prepared to do the proof. Half of you told me you already knew the CLT. So I'm just kind of curious, did you do this proof from the book? At the beginning of class, I asked, where did you guys leave off in probability class? You said the CLT.
I think we did do it.
You think you did?
Pretty sure, yeah.
You don't remember it though. Let's remember it this time. The only way you're ever going to remember something is by iterating through it. Seeing the steps, looking at it, and then I'll show it to you again. So if I do ask you to look at something in the book, for next time, pop quiz is fair game. So obviously I have to give you a little bit of a courtesy on how hard I graded it because I didn't tell you all the elements that I would grade on. But I might ask you certain things like figure out the MGF for that thing and show me how it simplifies, you know? So something like that, parts that we could go through. So I want you to be kind of on your toes. That is, we're going through this and I direct you in a direction, you follow through, you take a half hour, you read through the book, and then the sequence will make more sense. Does that kind of make sense? That's what I want. So eventually I'm going to enforce it. So not quite yet. I promise you, I will check to see if you know how to do this. What did I just say? I said something to you. This is a gift. What gift did I just give you? Elise? I want you to know the proof. But what did I just say when I said I promise you I will know if you know how to do it? David?
Did you want to ask a question on a quiz or exam?
Yeah, quiz or exam. I'm promising you the question. So every time I say that, I will know for sure if you know how to do this. I'm promising you on an upcoming quiz or exam. That should be a gift where you're like, yes, wow. You're only going to ask me like 10 hard questions. That's one of them. So this will be there. I really like this thing. There are other proofs. There are deficiencies to this proof, just like all of them. If you want to quibble about it, read through your book even more, read through their citations, take a measure theory class, take a few of them, and eventually you'll get to the point where they show the proof with minimal assumptions. And the only assumption we really need is an assumption on these XIs. So the XIs, IID, you don't need IIDness for central limit theorems to hold, but this version of the central limit theorem, we need IID. There are other incarnations. There are other limit theorems. We have tons of limit theorems. Lots of limit theorems that say that this test statistic follows some distribution. This one is a really important one. So lots of limit theorems. Lots of limits we take, lots of test statistics we look at, lots of asymptotic distributions that things converge to. So if this comes from some distribution, I'm not going to focus on the parameters, I'm just focusing on the probability theory. So I won't write down theta, but obviously there's some underlying theta, we're just not going to touch it, so I'm going to just remove it from the notation. So IID from this distribution, kind of doesn't matter what this distribution is, except we're going to need finite mean and finite variance. Bless you. So it's finite, it exists. Lots of ways to say that. Sometimes people just write less than infinity, and that's what they're saying. It exists, it's a number. So this is the only condition you really need. So in reality, for the central limit theorem to be true, all you need is that. And that's basically a condition on the second moment. So just remember, expectation of x squared minus expectation of x, all squared here, that is the variance. And so this is a condition on that second moment. If the second moment exists, your first moment is going to exist. So they're all bounded by each other. So that kind of makes sense. And you can just kind of think about the weight of things, what's happening in denominators and numerators. If you're powering up this thing, that's obviously going in the numerator of some expectation and kind of lifting the weight. So if the tail weight is heavier in the tails, it's going to integrate as well. I, of course, like to think about things conceptually, what's really going on, and then I like to think about how do I actually color that with a real proof. So this is all you need is this thing to be bounded for the CLT to hold. We're going to assume all kinds of things because we only have like 20 minutes to do the proof. I don't want you to do the 18-page proof that you basically do. The proofs are pretty impressive, and that's why you don't see them in books where they just assume this. So we're going to be making a stronger statement than we're proving. Okay. CLT to a lot of people just means x bar is approximately normally distributed. We mean something a little bit different than that. What we actually mean is x bar n minus mu over sigma over root n. This is going to converge to a normal 0, 1 as n goes to infinity. I could rewrite this a couple different ways, and it would be the exact same statement. I could get rid of the mu here and put it there. Same thing, it's equivalent to each other. I can just shift. I could also get rid of this right here. That shows up as a sigma squared right there. So when you rescale by something, you have to square it in the variance. So I'm denoting the variance over there. And this would be correct. This is not correct. You can see the problem with that. The n just went to the other side, and I was taking the limit with respect to the n, and I can't just throw it to the other side. So, as n goes to infinity, if I'm taking the limit on everything, it's not going to converge to that, and if I take the limit here, it's going to go to something degenerate with zero variance. So we want to put the n over here, root n, and then just for convenience, we might just look at the standardized statistic. Minus mu, put the sigma here, and just change those. So if you're gonna move anything to the right-hand side, make sure it's not the n. So, but this is what the central limit theorem says. This is true so long as I have finite variance for the distribution. There are proofs that are a lot easier that assume finite fourth moment. You know, that proof isn't too bad to get through. That's like a page in a measure theory book, and that's what I expect you'll probably see later on. Really, I just care that we're proving in some form. You have a version of a proof. It's not too hard to understand. There's some elements that are fun to test you on, and so it gives you some technical expertise too. All I really care is that we're converging to a distribution. It's normal. That's the thing that you're going to compute probabilities on. You're going to do something with it and report either p-values or posterior probabilities or something like that. So everybody adheres to the central limit theorem. This is just a probability scheme. We all like it. So we're going to assume that MGF exists. So we're making statements about all kinds of derivatives in things. So we're putting extra smoothness conditions to minimize the proof. Does anybody know where they first proved the central limit theorem? I mean, they just started like this and they did the full-blown proof, right? And showed like the strength of convergence. Maybe this is more than just a distributional convergence. Maybe they said it converges almost surely. They didn't do that. They took them hundreds of years to come up with that. They're still working on it. Where did they first come up with the central limit theorem? Where did you first learn it? I mean, it's like a long time ago, right? X bar normal, your high school teacher says, well, I'm looking at the average grades. I think everything is normally distributed, so I'm going to grade you based off of the curve. the curve. The curve is the normal curve. And I'm going to assume there's some number of percentages of A's, some percentages of B's, some percentages of C's, and you came back and said, that's an abuse of the central limit theorem. That is not true. You have no right to do that. Anybody ever say anything like that? Like, no, okay. I think that's like in our parents' generations or something like that. My parents' generations. It's nonsense because you're not averaging a class. You just have a snapshot. The CLT kicks in if you average the whole class's score and did that year after year after year with no overlap in the classes. We'll assume some sort of IID-ness, which is imagination, because generations have some correlation to each other. They change. It's not the same distribution. Every 4 years, the attitudes in classes kind of change. So that's been my observation. Every 5 years is a new era. So central limit theorem isn't kicking in for this thing. It's kicking in for the sum of the xi's, which would be a repeated experiment across years with no overlap, assuming that all classes are coming from the same population over and over again. All kinds of abuses of the central limit theorem. So when people invoke normality, you see people do it for like intelligence scores, the IQ of something, abuse, absolute abuse. Where did the CLT first come up? Just since we're filling in some history. David?
Okay, first, it was also the first period, it was for, just for binomial.
You got it.
Variables.
Yeah, so it's the binomial approximation.
They felt like it was true for more variables.
Yeah, exactly. So people always ask, like, how did people come up with this? It wasn't smooth. They did it for binomial. They were kind of looking at binomial coefficients, doing that Pascal's triangle thing, and noticing it looks like it's converging to something normal, and we see the binomial approximation sometimes with a normal. And that's what they were coming up with. They still didn't know exactly what a normal distribution was. The e to the minus thing, that took later, that took longer. So they knew it was some distribution, and they came up with that, and then they generalized, and they came up with these stronger proofs. So hopefully you understand what the templates look like, and you get into the templates, you start following the templates, and you can start reconstructing, and then after a while you might come up with a new wrinkle and prove something new. So just keep in mind, be patient with all of this. But there is kind of a template to what people do.
Was that revelation they made with the binomial distribution before Euler's time?
After.
Okay, so they knew about Euler's algorithm and stuff like that.
Yeah, after. So I think they knew that sort of stuff. They knew what E was, but not this distribution. They were still arguing about randomness. So in Euler's time, everything was just empirical. It was all, what's the word I'm looking, deterministic. So they weren't even thinking this way yet. That took until much later. So 1700s, they start grappling with this. 1800s is where they really start playing around with it. People started using the normal distribution to model different traits. They were saying, wow, it just kind of looks like these traits are normally distributed. So they started using normal distributions before they had proofs. So anyway, don't be fooled. This stuff comes out of somewhere. Where did we all learn it from? By reading our books, studying them, going to citations, reading more papers, and then finally understanding things. Okay, so we know what the preliminaries are. Finite variance will assume more things. So central limit theorem, we'll get onto it. We'll do this proof. Bless you. Bless you again. Okay, step one, we want to find the MGF for this thing right here. What I said is this is equal to sum of yi over root n, where the yi is just a standardized instance. So this is standardized. If you want to put square root of 1 under there, because it's just one sample, you can do that and see the same thing. But this is the standardized form for each individual instance. We can see that just by looking at sum of yi's. Let's just look at this first, do some algebra. So this is going to be sum of the xi's minus mu over sigma. I'm going to rewrite this. This is x bar n times n. That's just sum of the xi's. I'm distributing that sum across there. Minus mu times n divided by sigma. So I just slid this sum over the numerator. This isn't quite what we want. I'm going to rewrite this a little bit different. This is x bar n minus mu. I'll bring the n downstairs, and this is not the test statistic that we're looking for. It's a little bit off. That's just the sum of the y's. So if I want this thing to look like that thing, I need to remove one of the root n's out of this. That's where this root n is coming from. So if I divide this by another root n, there's two root n's there, one of them cancels, and I get back the original thing. So we have that this is equal to that. So this is kind of a nice thing. I'm just kind of generalizing this, shifting everything, rescaling it, so I know what the mean and the variance are. That's super convenient. So let's just think about this. The expectation of the y's, this is 0, it's standardized, so this is for each one of these things. That's an individual y, not the sum of the y's. The sum of the y's, the average of the y's also is mean 0, but I'm just talking about the individual y. And the variance for the y's is equal to 1 because everything is standardized. I will kind of point out this also means that the expectation of y squared, the second moment, this is equal to 1 as well. And the reason you know that is because the mean is 0. So let's just rewrite this. Variance of y, we know that that's 1 because it's standardized. And this is equal to the expectation of y squared minus expectation of y all squared there. We already know that that's 0, so the second moment is the variance. And we've standardized everything, so it has variance 1. So these are some things that we know of having a circle. So we're going to first find an MGF of this thing, but we're going to write it down like that. Let's just see some quick properties of MGFs. I think most of you remember this. These are easy to remember because they're easy to derive. You can see the proof in like as one line. So properties of MGFs. This isn't part of my proof. I will come back and utilize this, but I just want you to remember that these are properties. So I'll usually invoke a new random variable when I say aside. This is just something we need to know about distributions. And just arbitrarily, I'll pick a random variable that's usually not on the board. Sometimes I recycle x, or y, but I get a little bit confused when people start recycling variables that are on the board. So I'm just going to call this z. So anytime I say aside, new random variable, and I'll usually pick z. So let's just talk about the MGF. If I've got an MGF for, I'll call it random variable zt, that's just equal to the integral of zt fz, where I integrate over the whole space of z's. Usually I write that down as that, and sometimes I forget to write it down. This is a definite integral. MGFs are just functions of t. So if I've got an MGF, then I can start thinking about sums, properties of sums. So I could look at the MGF of some zi's, and I'm going to assume that the zi's are independent from this distribution. We will use that property. So the moment generating function is just going to be integral sum of the zi's times t, I'll just put that in braces, fz dz. I'm being a little bit lazy and I'm not putting in all my indices right here. I could, but I'm not putting down that this is a definite integral. I could. Let's at least write down that there's n of those things. So I can change this up a little bit. This is just, I'll just rewrite this, is the expectation of E sum of the ZI's times T. Same thing. I goes from 1 to n. This is equal to the expectation of the product, e to the ZI T. I can pull that product out of here. Somebody tell me, why can I pull that product out? They're independent. So if you just go back to the definition of the integral will factorize. So when I'm integrating over the ZI's themselves, I can factorize all of those because they don't have anything to do with each other. So they all factorize. So I can pull that thing out. I goes from 1 to n. This is independence. If you ever get confused on what the notation means, go back to the integral form and just start using what you know from calculus. So the integral itself factorizes. And so this is just equal to the product. I goes from 1 to n of this MGF, I'll call it for ZIT, right here, but the Z's themselves are identically distributed. So that's the other ID part. They have the exact same distribution of each other. Independence I used here. They have the same distribution, so they have the same properties, so they have the same MGFs, and we can just get rid of that I. And this just looks like the MGF for Z powered up to the n power. So for sums of random variables, the MGF is just the MGF of the original underlying random variable powered up to n. That's true for Fourier series, characteristic functions. That's true for lots of stuff. So you've probably seen this before. Let's just do one more aside. Let's do rescaling. So scale. Rescaling. I might look at the MGF for, I'll say Z over C. I think in the book they use times C, same sort of thing. If I can divide by C, I can multiply by C. It's the same sort of thing. Since we're dividing, I'll just re-butter this up and divide by C. So rescale means you either multiplied or divided by something, and those are exactly the same things. So this is just going to be equal to the expectation of E Z over C times T. So keep in mind my argument T refers back to that thing. And I can reshuffle this. This is the expectation of Z T over C. And I can just drag that C right in there. And so I can rewrite this, oh, this is the MGF of Z, but the argument is T over C. So this is the MGF for Z, T over C. And that's the rescaling. What we see here is we see a sum and a rescale. So we're going to use both of those properties. You could tell instantly who was who back in the probability class when you first saw this. And people are like, can I have a note sheet so I can remember that? It tells you instantly they don't understand what the operator is doing. So I don't allow notes in my exams. So I allow you a pencil or a pen, and that's it. So I want you to understand the reason and how to rederive these things. So anytime you see a formula, you ask yourself real quickly, could I redo that? Could I explain it? These ones, yeah, sure, you can almost see it. So but you want to get to a point where you can convince yourself, I know how to explain this to somebody. The best way to do that is to practice it. So you either do it with somebody, which is frustrating because they'll start interrupting you and asking you questions and say they didn't understand your step, your shorthand notation, but you can still play the game. I used to do it all through grad school. I had a whiteboard in my apartment, and I would sit there and I would pretend, and by iterating over these things, I memorized them. So that's the only technique I know how to memorize anything, is repeat, say it out loud, write it down. That was Friday night, right? Before you go out, you go to your whiteboard for a couple hours and start seeing if you know how to do hard problems and you can articulate them out loud. I think it's a really good exercise. We'll try to remember the expectation is 0 and the variance is 1, what I just erased. Well, let's come back to this MGF and start carving out this proof. So we want the MGF of x bar n minus mu over sigma over root n. I'll write it this way again so we can remember what we're doing. The standardized random variable and its argument is t. So we want that moment generating function. And what we're going to try to show, we'll show this converges as n gets big. I'm going to need to justify all those steps. That this converges to e to the t squared over 2. So just recall the MGF for a normal mu sigma squared. This is e to the mu t plus minus plus. This is the one that messes us up all the time. I feel like I need to see that minus sign. It freaks me out when I don't see it. This is one of those pluses. Plus sigma squared t squared over 2. So for a standardized random variable, that's 0 and that's 1, which brings us back to this. So this is the normal 0, 1's moment generating function. Let me just ask you a question real quick, because I front loaded you. Could everybody prove that? I went home and did it myself. Yeah, how do you do it? You don't need polar or anything like that. You kind of do if you don't know about the integrating constants of a normal, but all you have to do is complete the square. So it's a completion of the square exercise, and if you ever want to see that, we can do it in a review, but I'm kind of expecting you could do that. So it's just completing the square, and it's good stuff to know how to do. So I'd be more than happy to go in and fill that in at review session and chisel away at it. You see integrals like this all the time. So being able to wield them is half of getting an A++ in this class. Being fast. You can see it so that you can write it down quickly. Yeah, I did it myself. I spent 5 minutes, sat down. When I got home, I wonder how this is. I asked Dylan, how do you do it? He said, complete the square, I think. And then doing it was a different activity. Didn't take long at all. Okay. We'll just utilize that again. I'm not going to ask you to derive moment generating functions, but I do think they're good practice. Sometimes people ask me, where's some extra problems that I could practice? They're all through this class. Just reminders of how did we derive this stuff in the first place. So we're going to be aiming at this. So this MGF is sum of the yi's over root n t. Same exact thing. Now I'm gonna, and I'll just be clear. That's the sum of n IID things. So now I'm gonna use both of these properties. I've got a sum, so I'm gonna be powering up the original MGF to the nth power, and I'm gonna be sliding the scale factor into that part of everything. So this is equal to the MGF of the individual y's. Scale factor gets slid over. T over root n. Where is that getting slid over? It's just this part. I could have the sum of the yi's still if I didn't want to deal with that yet. So that's that. Now I can deal with the sum and put it back as the original IID random variable y and power this up to the nth power. So that's what the MGF looks like. And now we've got a little bit of work when we take our limit. We've got an n here, we've got an n here. Okay, part 2 of this proof is to expand this because we really don't know much about the MGF yet itself. We know the first moment, we know the second moment of it because we've standardized it, but we don't know anything else, so we're going to approximate it. So let's just work on this for a while. We'll approximate. So we'll apply Taylor's here. And then we're going to come back around and raise it to the nth power. We'll exponentiate after we have our Taylor approximation. So let's just work on the interior and then we'll think about that power. Let's not forget we have to raise it to a power. I had written down some things that were incorrect last time as we were doing the preliminaries. I'll just kind of point out where I made an error. So Taylor approximation. So we're just going to approximate this by looking at some derivatives of this function. I'll denote those by braces k in the power, so that's my kth derivative, divided by k factorial, and I need to center this somewhere. This is where I made a mistake. I put t over root n. This is the centering parameter. So if you wrote that down in your note last time and thought, where are we going with this? There was a mistake right there. So times t over root n, that's the argument right here. This is a polynomial in that, so this is a function of that thing minus the centering parameter. And then I'm going to raise this to the kth power. K is going to go from 0 off to infinity. Now we have made assumptions here that those things exist in the first place. So they don't always. There are distributions out there that I can't generalize through this argument, but maybe you can move to nether transformation. The characteristic function instead of an MGF is a possibility that'll extend a whole nother class of functions that you could do this proof on. And if you want to extend further, you have to wait for your measure theory class. But I am making some assumptions that these things even exist. And because I'm writing them all down and thinking about them all, I'm saying that they all exist. So this is too strong of a statement. We need only the first two of them to exist. So I should just be clear. We need the 0th one to exist. That one always exists. We need the first one and the second one. So we need 3 of those terms in there to exist, but we also have to deal with the remainder in everything, and we need to think about the existence of that remainder. So this proof is assumption steeped, but it's still an elegant proof. It's still pretty cool. And it gives you all the steps you need to understand some of the higher level proofs. Okay. So, question. Let's see. So that determines kind of in which areas we're going to try to converge, where we're centering our approximation. So the approximation is good around C, but we know something about this. We're looking at this statistic right here, and we know where this is centered around. It's centered around 0, and that's the bulk of things. A lot of times I wouldn't take that as the argument that everything's centered around 0. That's where I should center everything. I need to know that the mass is centered around there, and it's not like multimodal when 0's in the middle. So I wouldn't center something if you're a multimodal, but this is all compacted and dense near 0. It's a normal distribution. So we'll pick 0. Since x bar n minus mu over sigma over root n is centered there. I'll say it's concentrated. Where else will I center this thing except for where it's all concentrated? So we'll change this to just m y t over root n. This thing is just going to be m0 centered at 0 over k factorial over 0 factorial plus m1 0 over 1 factorial This is going to be t over root n. It's my first polynomial term, the linear term in t. M2, 0 over 2 factorial t over root n minus 0, if you will. I'm going to leave it out, squared, plus some other terms. So I'm going to call this the remainder. So all we're going to use in the approximator are those first 3 terms. So I'm going to say this is the remainder of y, and I'll give it the exact same argument. Just remember what that looks like. This is just going to be k goes from 3 off to infinity, mk centered to 0, k factorial, t over root n raised to the k, where the powers start at 3. We'll analyze that a little bit later and see what's happening with those powers. We can't just ignore them. So I would say, if you forget about this on a qualifying exam or something like that, if you're a Stat PhD student and you just say, I never really liked remainders anyway, I'm marking you way off on it. If you just toss the remainder and say it doesn't matter. I want you to keep the remainder around no matter who you are in the class. So the level at which you're able to argue that this thing doesn't matter is going to kind of distinguish you. So I want this class to be, relevant to non-PhD stat students. So you don't have to go through all of the steps to prove that this thing, the remainder doesn't matter, and I'll kind of tell you kind of the level you need to argue. And I'll try to distinguish this from qualifying exam bill. So I know that word gives everybody shudders in a class qualifying exam. It's not that hard. I'll tell you exactly what I want to be able to see if I ask you a question about the CLE. Okay, so we've got this thing right here. We've got some of these terms. So I already claimed that this is 1, this one's 0, and this one's 1. We did that last time in the prelims. At least I asked you to hone in on this right here. Remember, these are just these moment generating functions for y right here. So which random variable am I thinking about? I'm thinking about y, the yi's themselves. Just the transformation of each individual xi. Subtract off the mean, divide by the standard deviation, sigma. So this is 1, simply because this thing, no derivatives, I'll say of whatever this is, y, t, f, oops, just that. This is just going to be e to the y t fy dy right here. I'm not taking any derivatives. I don't have to slide the derivative operator across there and do anything to it. All I have to do is evaluate this at t is equal to 0. So that ends up putting a 0 right in here, and this whole thing becomes 1, and then I'm just integrating over the density function. Density functions add up to 1. Why? Because we had to add up to something. 1 is easy to remember. So we know that one. We know this right here because the expectation of y is 0. So that is the first moment. That's just what it is. It's the first moment. It is the expectation of y. So what am I doing to this function? I'm taking one derivative over this, it's popping down to y. Then I'm evaluating t at 0, and it's dropping that out to 1. And so it is the expectation, and by design, we've made the expectation 0. Similarly, this is the second moment. It's not the variance, but in this special case, it is the variance, because when the expectation is 0, the second moment and the variance are the same. That's what we wrote down before. So this one right here is because the variance of y is equal to 1. So now we have something we can work with. Let's get rid of that. And that's all we know about f right now. That's all we know, so those are the only coefficients I can really label. So m, y, t over root n is going to be equal to 1. 1 divided by 0 factorial is still 1. So this is 1. That's 1. This one's 2. After that, they get harder. So the next one is 6. So 1 plus 0 times t over root n. So that's my coefficient there. I'm not dividing by 1, but I'm multiplying by 0 if you want me to. So I can divide by 1 there, I can divide by 1 there if you'd like. Plus 1, that's my coefficient here, divided by 2. 2 factorial, I'll just write it in as 2. This is t over root n to the second power. And then I've got some remainder stuff, plus remainder. We'll look at this remainder in a little bit. So just keep in mind that starts with powers raising it to the third power, and that's important. I need to understand how good of an approximation this is. So what we said last time is I need to compare the remainder to the approximator. And all we really need to look at is the largest term in the approximator to the smallest ordered term in the remainder. So they all bound each other. So it's not that you end up looking at the 117th polynomial term and all of a sudden your approximation gets way better. It's incrementally getting better. Okay. If you're not satisfied with that, and you go, I need to know more about that, I need to be able to prove it, you want to be a number theorist. That is where you're aimed at, that's where your passion is. If you go, yeah, I get it, then you're not a number theorist. Okay. So we've got all of this stuff right here. I want to look at the remainder. And check convergence. What I want you to do is do the same thing that I see journal papers do. Talk about what you need to check, and then write down the formula and kind of give some explanation. So this is a good statement. I want to check convergence. Okay, checking convergence did not just throw away the remainder. So if you just throw away the remainder in this class, I'm going to mark you off a couple points on a midterm or a final. If you do this on a qualifying exam, you're going to get hammered for it. This is what I'm asking about, is you just being able to do the details. So you can say a statement like, let's check convergence. So how do we do it? We compare the approximator to the remainder. So it's relative to something. How big something is or how small something is a comparative thing. So you always have to compare. So when somebody says something's good or bad or big or small, you need to ask the question, compare to what? So it's always a relative. So I'm going to look at the remainder, y, t over root n, and I'm going to compare it to the largest order term in the approximator, and that's this thing. You would probably agree that half and those sort of things don't make it different. There's just constants when I take the limit, but I can write it in anyway. So t over root n squared, it'd be very common for somebody to just ignore that because it doesn't change the limit any. But this is the largest order term in the approximator, so I have to compare how fast this thing is exploding compared to that. And I want to show that this thing converges to 0. So we want to show. So that's as n goes to infinity. So we're kind of changing the convergence property. We're not focusing on the radius of convergence. We already know we're in that radius close to 0 somehow. And we're focusing on n because as we take n bigger and bigger and bigger, it's pushing us closer to 0. So as n goes off to infinity, what does x bar minus mu do? It is 0. So it gets there in the limit. So I'm not thinking about that radius in terms of how I've centered everything, because I know I'm in that radius. I'm thinking about controlling that, how close I am and how much I'm in that radius by cranking up n, because our test statistic, our standardized x bar is getting closer to 0. How do we know that? That x bar minus mu is getting closer to 0. Please don't say the central limit theorem, because that's what we're trying to prove.
Weak law of large numbers?
Yeah, law of large numbers, you take your weak one, you take your strong one. What's the difference? One's a statement about moments, kind of like this, and one's a statement about what happens to the actual random variable almost surely. I don't need you to distinguish that, I just need you to know the law of large numbers, some form that says x bar goes to mu. So that's what averages do. So we're going to look at the limit in terms of n right there, because we're already inside that radius of convergence as n gets relatively large. We don't need to take it all the way to infinity to get there. I could put all the other lower order terms in there. If you're wondering, why don't I just put the whole approximator down in the denominator? It's because everything is just going to be controlled here. This is going to be the asymptotics that controls whether or not this goes off to infinity, not the other terms. So you can just get rid of those. And in fact, I don't even have to put the whole remainder up in the numerator. All I need is the smallest order term. But let's just kind of look at this and convince ourselves. So this thing looks like this. So I'm going to just write out those terms in terms of k. I'll just start this off. This is going to be t over root n raised to the third power. If you would like this other stuff in here, m3 0 divided by 3 factorial. No limit's going to have anything to do with that term right there. So plus m4, fourth derivative, 0, divided by 4 factorial. Again, these things don't matter. It's just where the n appears. So I don't even have to write those down. I could have just gotten rid of all of them, but it's good to see the whole idea. So plus dot, 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 dot. What you'll notice is that in these denominators right here, that's where n appears, and I'm powering them up higher and higher and higher. So as I start powering something up that's converging to 0, I converge that thing to 0 faster. So we're going to come back around to this idea. So if I have a number 0.01, I power it up to 5, it gets smaller. I power it up to 10, it gets even smaller. So let's look at this. Divided by t root n squared right here. Divided by divided by, I guess, this 1/2 in here. They don't matter, that part. Not part of the asymptotics. What happens to all of this? This is going to be proportional to, so I'm going to get rid of some constants. I'm really just getting rid of that constant because I'm sick of looking at it. So what happens right here is the n gets kicked up to the top, that's square root, and it's being squared. And I'm multiplying that, and if you'd like the t down there, you can have the t down in the denominator. That's this t, that's t squared. Again, we're not taking a limit over it, so it doesn't really matter to us. And then I've got these terms, t cubed over n, and I'm going to write it like this, 3/2. And there's some constant in here, and I'm just going to say some constant, I'll call it C3. Again, we don't need to look at it. That's just this part. So plus T4 divided by N, 4 divided by 2, so that 4 appeared here, times some other constant, so on and so forth. But you get the pattern, is these are getting powered up right here. And so it's making them bigger, which in turn is making that whole term in the sum smaller. So we can already see limit n goes to infinity, n times our remainder, so this is just n times the remainder. If you want to put the t squared down there, you can. Again, it doesn't matter. So this is y t over root n. This goes to 0. So this thing converges. So the remainder is small relative to the approximator. And as n gets bigger and bigger, the remainder is just tinier and tinier compared to the approximator. So that's what we need to do to check convergence. Now all we need to do is just finish everything. So we've checked convergence, it looks like it'll converge. This is maybe an adequate approximator. I probably wouldn't use it in practice, but for proving something, you know, as a concept, I think it's useful. So now we just need to do the last part, and we'll finish this next time. Remind us how we got here. So finishing will entail that we end up looking at the moment generating function. This is going to be our powered up thing because we've got our sum. So I'll build power. We've been dropping that. So I've dropped this part and focused on the individual elements and not the sum itself. And this is just going to look like 1 plus 1/2 this term, t over, I'll put t squared over n, plus our remainder, root n. We have to understand what that limit looks like. The book does something for us. They pull that n right out. They put that n here, and they write it out like this. We're going to study this limit and talk about it when we come back next time. Keep in mind, as I power this thing up, this thing inside of the power is going to 0. Now, I never like arguments like that it's like, okay, something's going to 0, so I can just vanish it. You've got to think about this wrapper that we put on it and what it's doing to it. I want you to think about polynomials, because that's all this is. So it's just polynomials. What happens to this term? We don't care about that 1 right here. Maybe you want to think about it. But what happens to this polynomial as I start powering this up? The easiest way to think about this is take the power of 2. And all you'll ever see is you'll see these terms in a linear form pop up, and you'll see them pop up in powers in the polynomial. If I take n to be 3, something bigger, you're going to see the linear term pop up, and you're going to see it pop up in powers. A quadratic term and a cubic term. So if that thing is small, when I power it up and expand this thing, all the other terms are just getting smaller and smaller and smaller. So it's the linear version of this term that's the biggest term right there. And that's going to 0, and by powering it up, it makes them all go to 0 faster, all those powered up terms. We're going to come back and talk about that. There's a lemma in the book that says something like this. I think this is in chapter 2. So it's going to say limit n goes to infinity. This is going to be 1 plus 1 over n, alpha n to the nth power right here. This is going to go to e to the alpha, where the limit n goes to infinity, alpha n goes to alpha. I almost see this as obvious because when I think about this, I just think about a polynomial expansion. And they give it a lemma and they tell you there's a proof. It's not Slutsky's theorem. It kind of looks like that, but it's not. It's something different. But I tend to think that this is fairly obvious. That's why I'm not a mathematician. Yeah, right. Of course that's true. So why? Because when I expand out that polynomial, all those terms are getting shuffled around, powered up. They're not blowing up, they're shrinking when I do the expansion. And so you really just have to think about this limit in the linear form. We'll come back next time and show when we converge this thing, this is our an right here. What is this converging to as n goes to infinity? This part is just going to t squared. So we'll slow that down next time and show that this thing is t squared over 2. So it's just, that 2 is in the wrong place. Sorry. It was magic before, that was the non-magical removal. So the 2 goes there. So it's just converging to this part right here, is that stuff. I want to spend 5 more minutes talking about that convergence and what I would like you to talk about on a midterm or a final. The lines you write that I go, oh, they're talking about those lines, that's cool, they know what they're talking about, moving on. And if you go to journal papers, they do the same thing. Oh, they made the correct citation, they cited this, moving on. So theory is a template. You know, at least nowadays it is. You can program ChatGPT probably to carve out your proofs because a lot of them look the same. So I will say you can use ChatGPT anywhere in your life, but if you're wrong, you take all the blame. So that's how I feel about that thing. So if you touch it and you're wrong, you don't get to say, but, here's why I'm wrong. No, you are wrong. So let's talk about that a little bit when we come back to so ethics of these things. But I do think that this is almost programmable, doing theory sometimes. It's novel theory that's not programmable. Okay, cool. Let's come back next time, finish this proof, show that the CLT is true, at least in some moderate version of the proof, and then we're going to move over to the delta method. The delta method, the way they explain it to you in the book, is just a probabilistic thing, and I'm going to show you how to use it for inference. And then later on in the class, I'm going to have you do a simulation study with it. I'm going to have you compare the delta method to the bootstrap, another technique you can use to do inference, and then I'm going to teach you about Bayes. So before we jump into chapter 6, I'd like to say some stuff about Bayesian statistics as well, so I can give you some Bayesian exercises. Again, I think this class is about comparison. So comparing different techniques to each other and seeing the relative performance. That's it, you guys. Thanks so much. I will see you on Friday. We will do a preliminary day on the delta method as well. So we'll do kind of a fast preliminary, I'll tell you the things you need to know, and then we'll roll into the hardcore proof. So I'll give you kind of the light version and then the heavy version. No review session tomorrow. I don't think we're ready. Let's postpone for one more week and we'll come back not this Thursday, but next Thursday for review. Is that? Okay, that sounds good. And then if we need to start moving up to weekly, let me know. Thanks so much.